Today we're going to be learning about optimization. In order to do optimization with calculus, you need to already know how to find derivatives. If you can't find the derivative of a function, you won't be able to optimize using the methods I'm about to show you. You will also need to be able to sketch functions. So that means that you will need to be able to find stationary points and find x and y intercepts. Not every time, but they're certainly helpful when sketching the function. So optimization, if you're in Queensland doing 11 Maths B, you'll be looking at optimization in modeling and problem solving questions. There's lots of reasons why you might need to find a minimum or a maximum for a function. So a couple of examples might be if you were to be looking to maximize the growth for a crop, obviously you want to use the least amount of water or fertilizer or things that cost you money in order to get the maximum amount of growth, so profit. So it might be easy to come up with a function and look at your graphics calculator, for example, and see those points, but in real life we need to consider other things. So for example, you might make the assumption that more water means more growth. Well, unfortunately we don't have infinite amounts of resources, so we have some limits, I suppose. So we do need to keep domains in mind. So for this particular one, it's a car where if you were trying to drive a long distance for that particular car, what speed would you want to go at to minimize fuel consumption? So in this case we can see here it would be around 80 kilometers an hour, but we'll find out these things using algebra to be sure. So when you solve optimization questions, we learn a little strategy called cubed. Circle the numbers, underline important information, box the actual question, as in what does it want you to optimize, eliminate unnecessary information, and draw a picture. So for us, drawing the picture will be our graph. We need to think about variables. We need to optimize using two different variables, or optimize one variable when thinking about the other. A lot of the times you'll be given a relationship as in the function, but if you're not, you need to come up with one. So there will always be enough information to do so. We talked about having two variables. Okay, so which one needs to be optimized? And that needs to be the subject of our function. We talked about all of the stuff that we'd need before, so being able to find stationary points, etc. And then finally we should be able to come up with our answer. So here's an example. The electron emission, that we're calling E, from a particular surface that has been exposed to radiation for a fixed period of time depends on the frequency, which we're calling F, of the radiation, and it is approximated by the function there, where E and F are measured in appropriate units. Find the frequency of the greatest emission in the domain 2 to 7. Okay, so this is a good example, say, that we're going to ignore everything outside of this domain. So we're lucky in this regard because they're saying find the frequency of the greatest emission, and it's already set up that that's the subject of our function. Okay, so first thing we need to think about here is coming up with some sort of sketch that's going to help us find in this case, the greatest emission that falls within these domains. So the first thing we're going to do is we're going to find the derivative. So if you're not sure how we've come up with that, you need to go back and review your derivatives. So that's not a topic of this particular video. So now that we know our derivative function, we can whack in our 0 to find our stationary point. So the gradient, where any minimum or maximums will occur, or inflections, will be 0. So in this case, we'll notice that 3 is a common factor across them. So we can factorize that out. And then we can, again, factorize the now monic quadratic. And using null factor law, we can see that the F, which is our frequency of the radiation, must be 4, because 4 minus 4 would be 0, or 6 minus 6. Okay, so it's basically telling us that there are two stationary points, so we'll need to investigate whether they're minimums or maximums. All we've done here is we've said, well, where f equals 4, we've subbed it back into our original equation or function, and it's told us that the emission would be 12. So where the radiation is 4, the emission is 12. Where the radiation is 6, the emission is 8. So we've just subbed it back in. Here's a little table just helping us to get a better idea of what we're looking at. So I'm going to start with the 2 points. So 4, 12 and 6, 8. So the first point, if we're looking at the gradient at that particular point, we know it to be 0. That's how we found the 4 in the first place. So we know it's stationary. So there's basically our 2 points. Okay, so we want to look and say, well, is this point a minimum or a maximum? So what we do is we go to a little to the left of the 4. So in this case, we've subbed in where f is 3, and we've found that the gradient comes out, so the derivative, the gradient function has come out to be a positive. Okay, so it's increasing, so we know it's coming up. Then we're coming to our stationary point. We've looked a little to the right of 4, so in this case we subbed in 5, and it's come out and showed us that the gradient where f is 5, the gradient will be negative, so -3. So we can see that this particular point, 4, 12, is going to be a maximum. We did the same thing for the next point, 6, 8, and again we already knew this one here to the left of 6, looking at 5, would be a negative. We found our stationary point a little to the right, so we've subbed in 7 into the gradient function and the derivative, and we found that that one's going to be a minimum. So we could do our sketch now. So I've cheated obviously because it's a little hard to sketch on the screen, but we've got our 2 points. We know there's minimums, maximums. We could have also looked at our x-intercepts using a cubic function. We would rely on our technology in Maths B. Okay, so we could have typed that into our graphics calculator. We'd be seeing something very similar there. The important thing is here it's told us we're only allowed to look between 2 and 7. So it's a good idea to try and highlight that to yourself by, in this case they put some dotted lines on there, so we're only really looking in between 2 and 7. We need to find the frequency of the greatest emission. So we can see here, well, at this particular point we're getting quite high, so that could be a possible point. Alright, so we will need to investigate that maximum a little more. But we'll also need to be careful that over here, when we have a frequency of 7, we can also see that it's going to be fairly close. So we need to investigate both of those. So we can do that now. So we already knew that when we subbed in a frequency of 4, the emission was 12. We could see that from our maximum point, but we needed to check what was going on here when the frequency was 7. So if we sub in 7, okay, again into our original function I'm referring to, we can see that it's also returning an emissions of 12. So in this particular case, there are 2 points where the emissions are greatest, at 4 and at 7. One more example. So in this particular case, this might look like another fairly straightforward one where we're given a function, but we've got to be careful, and there's a little trick in this one, and we'll see if we can catch it as we go. So there's a farmer stocking a lake with fish, trying to make some money. The more fish placed in the lake, the more competition there will be for available food, so the more slowly the fish will gain weight. From previous experience, it's known that when there are n number of fish per unit area of water, the average weight gain of each fish in grams during the growing season is given by the function. What value of n, so the number, will lead to the maximum total production of weight in the fish? So we're going to be really careful here because it's talking, there's a key word in here, each fish, but we're not talking, the final result is not asking about one fish, it's asking for the whole lake. So we're not talking about one fish, we're talking about all fish. So when they're asking about how many fish, we've got to be really careful here, because at the moment our function doesn't tell us for all, it just tells us for one fish. Okay, so we need all the fish in the lake. So what are we going to do? Well, if this is one fish, Okay, we can look at the total number of fish by considering the number they all are together. Okay, so not only do we have our original function, which was 600 minus 30, we're now multiplying that by the total number of fish in there to get our production, P for production. Okay, so from then on, very similar to the last one, we're going to find, expanding out. Oh, the other thing is we can already tell what type of function or what we're looking at in our graph in terms of a sketch, because our quadratic attached to our squared, we can see that the value at the front is a negative. Okay, so negative a value, which negatives will always give us a maximum. We found the derivative. Okay, subbed in 0, which is our stationary point. So we're about to find this point up here. Done a quick little factorisation, and again relied on our null factor law. So to make this equal to 0, n would have to be 10. Alright, so the stationary point is 10. What we've done is sub that back into the function, and this function over here, because we are looking at all the fish. Okay, so we subbed 10 back in over here, and we've found that we would end up with 3,000. And you'll notice down here our answer has gone back to relate to the units we were given with. The first example did not give units, it just said appropriate units, I think was the word, but in this case they're saying that we must keep in mind that the weight is in grams. So to recap, what do we do? The best summary advice I can give you is to come up with a sketch first. Really consider your domains. You can use derivatives and stationary points obviously to help you do that, but as the questions get a little bit more complex, they will start to get a little more ambiguous about the information. So going back to some other little tricks like cubing your question can be a great idea, but in the end you do have a graphics calculator, and I would absolutely recommend, at least if you can't come up with a sketch yourself, you should be using your graphics calculator just to visualize what you're looking at, which is going to help you know where to start looking.